In this problem, we have a uniform slender rod of 8 kilogram mass. It is pinned at the point O. And we also have a 5-gram bullet that shoots into the rod with a speed of 600 meters per second, and it becomes embedded in it. We need to determine the angular velocity of the rod immediately after the bullet becomes embedded. So let's imagine what happens after the bullet shoots into the rod. The rod will swing up in a counterclockwise fashion, which means that if we draw the free body diagram of the rod after the bullet has embedded in it, we will have weight force WR, the bullet has weight WB, but also we will have two support components at point O, OX and OY. And we will have linear velocity here. This is let's call it VG, and also linear velocity VB2. This is the second state. Initially, VB1 equals to 600 meters per second. So this is the VG2, second state. And also we have an angular velocity of omega. Let's call it omega 2 for state 2. Omega 1 is 0. Initially, this rod is at rest. Okay, so we cannot solve this problem by applying the principle of linear impulse and momentum, because OX is an external force along the horizontal direction, and at this point we do not know what it is, and we do not know how much impulse it creates during this process when the bullet becomes embedded. However, if we summarize the angular momentum about point O, then OX has no moment about point O, therefore creates no impulse about point O, and there's no other external force that would create moment about point O, in other words, creating impulse about point O. We do have horizontal forces between the bullet and the rod, but they become internal when we treat the bullet and the rod as one system. With that said, the total angular momentum about point O at the first state, initial state, equals to the total angular momentum about point O during the second state. And this is the equation we're going to use to solve this problem. So initially, the slender rod is at rest. The bullet has linear momentum of mb vb1, and about point O, where we have a moment arm of, let's call it dB for now. Okay, it's actually 0.8 meter. So this is the total angular momentum the bullet has initially about point O, and then after it has become embedded into the rod, we will have angular momentum caused by the linear momentum of the bullet. So again, linear momentum, moment arm, plus the angular momentum of the rod. In this case, because we have rotation about a fixed point, therefore the angular momentum of the rod about point O, which is the center of rotation, simply equals to IO omega 2. So now let's substitute numbers in. Initially, so the mass of the bullet is 5 grams, so 5 times 10 to the negative third power kilogram to be consistent with units. VB1 equals to 600 meter per second. dB equals to 0.8 meter. On the right hand side, we have 5 times 10 to the negative third times VB2 times dB is again 0.8 plus IO. This is a mass moment of inertia about the edge of this rod, which equals to 1/3 ml squared. So m is 8, L is 1 squared times omega 2, which is also an unknown. However, because this is rotation about a fixed point O, therefore from kinematics, we can determine that we can express VB2, which is the linear velocity of this point on this rigid body, because they have become one system now. And that simply equals to omega r. Therefore, omega 2 times r. R is from here to here, and that is 0.8 as well. So this together is VB2. Multiplied by another 0.8, which is the moment arm. Even though they are the same distance, they have different physical meanings. Plus 1/3 times 8 times 1 times omega 2. So here, as you can see, we have one equation and only one unknown, which is omega 2. We are able to eliminate the other unknown VB2 based on kinematics, because we know that when for a rigid body going through rotation about a fixed axis, the linear velocity at any point equals to its angular velocity times the distance from the rotation center. So from here, we can solve for omega. And that equals to 0.899 radian per second.